So good evening, Ireland. It's a pleasure to be back to talk to you about the end of everything. As you can see from the subtitle, I'm talking about the fate of the Earth, the Sun, the Milky Way galaxy, and ultimately the rest of the universe. So we're going to travel, in a sense, to eternity, well, perhaps not beyond, but from here to eternity. So I'm going to give a little bit of an introduction and then talk about the future in the shorter term of the Earth and the Sun and the solar system, and then think about the far future and the fate of the Milky Way stars and other galaxies, and then think about the far, 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 far future and the ultimate fate of the universe. That might sound a little bit depressing, so I'll finish with an epilogue on a slightly more upbeat note. So the story so far, let's just get some context. In a different talk, I talk about how the universe began, the beginning of everything. I'm not going to cover all of that material, but just in a nutshell, the universe started because we know the universe is expanding. We can run the clock back and determine that the universe, everything in the observable universe that we can see, used to be a lot closer together. At the moment, the observable universe is some 100 billion light years in diameter, but all of the objects we can see inside that volume used to be a lot closer, essentially just centimeters apart, separated by no more than the size of a golf ball. The early universe made an awful lot of stuff. In particular, it made a great deal of protons and neutrons, which ultimately led to all the hydrogen and helium that we see in the universe today. So what I'm going to be doing is looking not at the past, but at the future from now in years to come. But of course, thinking about years or thousands of years or millions of years, we're soon going to run out of zeros. So I'm going to be using these numbers along the top of the screen here to keep track of where we are. And each one of these boxes represents a time 10 times further into the future than the previous box. If we didn't do that, it would rapidly get out of hand. So what I mean is we're going to be looking at 10 to the 1, 2, 3, 10 to the 3 years into the future is 1,000 years hence. 10 to the 6 years into the future, 1 million years, and so on. 10 to the 9 years, 1 billion years. 10 to the 12, 1 trillion years into the future. And most of the slides in this evening's talk will have one of these red boxes somewhere on that top line to give you an idea of how far we've got. And I'm indebted to the work of Adams and Laughlin, who published a little while ago a paper on which they predicted the timescales on which many astrophysical phenomena are likely to occur. And I've used that paper as a way of sort of getting my slides in order. I'm not going to be dealing with topic by topic, although I might have implied that in the introduction. I'm not going to be talking about the Earth, then the Sun, then the galaxy. I'm going to be dealing with strict time order, and we'll see what happens when. Okay, let's jump. I'm not going to bother with the next 10 to the 1 or 10 to the 2. The next 100 years, let's assume that we don't blow ourselves to pieces. Let's assume we get climate change under control. In 1,000 years, we can predict that the Earth will have slowed down because of the effect of the moon tugging on the Earth's oceans. The Earth is slowing down and the moon is robbing the Earth of some of its angular momentum. At the moment, because of the Earth's slowdown, we've added a leap second every once in a while. Leap seconds would need to be added in the future, not once every few years, but in 1,000 years' time, leap seconds would need to be added to our clocks every few weeks in order to keep our clocks in sync with the rotation of the Earth. And it's not only the speed of rotation that's changing, the angle, or at least the direction of the Earth's axis, is going to change. Even if its tilt remains at 23 degrees, it precesses. In other words, the Earth's axis points at a point in the sky which is tracing out a very large circle. And we know that this occurs on a timescale of about 26,000 years for one complete cycle of precession. And that means if we look at where the Earth's axis is pointing, at the moment on the right hand side, that's where it's pointing at the moment, towards the star Polaris. It just happens to be within a degree or so of the Earth's axis pointing. But in another 10,000 years or so, the Earth will be pointing in a different direction. It'll be pointing over towards Vega. So Vega will become the pole star. So some people are of the opinion that the pole star is one of the brightest stars in the sky. Well, in 10,000 years, it probably will be. So one consequence is it'll make it very easy for Boy Scouts to point out which way is north. Just find a bright star, that's probably north. But there are more serious consequences of the pole star changing. At the moment, we are nearer to the Sun, i.e. at perihelion because of the elliptical orbit of the Earth around the Sun. We're nearer to the Sun in January during northern winter. But if the Earth's axis is pointing in the other direction, we will be nearer to the Sun during northern summer. So the distance to the Sun will be less when the Earth is tilted towards the Sun. So seasons will become more exaggerated. There will be changes to climate on a timescale of 10,000 years or so because of the way the Earth's spin and the Earth's orbit interact with each other. Now, variations in the Earth's climate due to changes either in the Earth's spin or the Earth's orbit are collectively called Milankovitch cycles, and we'll be seeing more of those in just a little while. On a timescale of 10 to the 5, 100,000 years into the future, the Voyager spacecraft are going to pass by nearby stars. If you remember, Voyagers 1 and 2 were launched in the 1970s. They explored and photographed planets and their moons, planets such as Jupiter, Saturn, and then Uranus and Neptune. Because of the gravity assist obtained by these spacecraft, they gained speed and ended up with velocities great enough to leave the solar system. In the top left of this diagram, you can see Voyager 1 heading off, and in another 30 or 40,000 years, it will pass the star system called Gliese 445. At the bottom of the image, Voyager 2 is heading off in a different direction, and on a similar timescale, it will pass the star Ross 248. Now, the Pioneer 10 and 11 spacecraft, they were launched a little bit earlier, but they didn't get quite the same gravity assist. They're not travelling quite as fast. They'll take a little bit longer to leave the solar system. Pioneer 10 on the right there is heading off in the direction of Aldebaran, and Pioneer 11 on the left is heading off in the direction of the centre of our galaxy. Still on a timescale of 100,000 years into the future, we know that there have been repeating cycles of glacial and interglacial, in other words, ice ages and the periods between ice ages, on timescales of order 100,000 years or so. We've got that from the Earth's record, the geological record. And as the Earth entered an interglacial, a so-called warm period, relatively recently, the next ice age is probably due on a timescale of order 100,000 years. We can't predict them exactly, but it's that sort of timescale. And this is another manifestation of Milankovitch cycles. On a time period of 100,000 years into the future, the Moon will continue to slow down the Earth. And leap seconds, if we wanted to continue adding leap seconds to keep our clocks synchronized with the Earth, because the Earth is slowing down, we would now need to add leap seconds, not once every few years as we do now, not once every few weeks, as I mentioned earlier. We would need to add a leap second approximately once every day. In other words, the length of the rotation period of the Earth relative to the Sun would be approximately 24 hours and 1 second. And so we'd have to choose one of the minutes during the day to have 61 seconds in it in order to keep the clocks synchronized. We don't know when stars are going to go supernova, but we think it's very likely that on a timescale of 10 to the 5 years, still 100,000 years into the future, we will probably see a supernova in our galaxy. For instance, Eta Carinae, or Eta Carinae, is a very massive star which appears to be very unstable. This is an image taken by the Hubble Space Telescope, and it was the astronomy picture of the day back in 2019. It looks like the outer layers of this star are very unstable and have been shrugged off by this star. Perhaps that's an early sign that it's not far away from being a supernova. So we can't predict these things, but we can get a rough idea, statistically speaking, of when they're likely to go off. On a similar timescale, we might see Betelgeuse go supernova. This is an image of the night sky taken over Czechoslovakia, in which the photographer has taken a very nice image of the night sky and then artificially brightened Betelgeuse to give us a taste of what it might look like when Betelgeuse decides to explode. Remember that these stars are close enough to us, only a few hundred light years, such that when they do decide to go off, they will not only be very bright objects in our night sky, they could very easily be visible during the day. But it's not just supernova that cause us potential problems. Wolf-Rayet stars, for instance Wolf-Rayet 104, these stars have very strong stellar winds and often are rotating very fast. This particular one is 7,000 light years away, and that might sound like it's far enough that it will be no threat whatsoever to Earth. If we can survive Betelgeuse going supernova at a distance of a few hundred light years, why should a star at 7,000 light years cause us any concern? Well, the death of this star might result in a radiation burst, perhaps a gamma-ray burst, even more powerful than a supernova. Because of the mechanics and the dynamics of these systems, very energetic jets are produced through a mechanism that we don't fully understand, but it's related to the rapid rotation of the star. And if one of these jets is pointing towards Earth when this star dies, then the amount of radiation being directed at the Earth could be significant. It's been calculated that if we were lined up directly with the jet when the star dies, then it could, in principle, end life on Earth. But the chances of that happening are not particularly high, because we would need an extreme chance alignment of the jet with the direction of Earth. Far more likely it's going to miss us and not cause any particular threat. 1 million years into the future, we know that our Sun is orbiting the Milky Way, orbiting the centre of the Milky Way, the same way that most other stars are doing. The spacecraft Gaia has been mapping out a lot of stars in our neighbourhood, and we are all orbiting essentially independently around the centre of the Milky Way galaxy. And because we're orbiting independently, every once in a while we are going to come close, just coincidentally, we are going to come closer to some of our neighbours. And it's been calculated that Gliese 710 is a star that's going to happen to pass very close to us in about 1 million years' time or so. As seen by us, it's going to look like Gliese 710 comes in and then goes out again. It's not quite that orbit. Remember, we are independently orbiting the Milky Way galaxy. But Gliese 710 is going to come close enough such that it will actually enter the Oort cloud, the large cloud of icy bodies that are surrounding our Sun at immense distances. And when Gliese 710 does come into the Oort cloud, it will certainly disrupt the Oort cloud by providing another gravitational source, and it will probably result in lots of objects raining down into the inner solar system, resulting in bright comets, perhaps for 1 million years or so. When Gliese 710 is inside the Oort cloud, it's interesting to note that for a while our solar system will actually have 2 suns, just like various other planets and moons that we know about. Still on a timescale of 1 million years into the future. Is this picture of meteor crater Arizona supposed to imply that we can expect an impact like this once every 1 million years? No, they're far more common than that. This picture reminds us of a couple of things. One, it reminds us that wasn't it lucky that this impact just missed the visitor centre by just a sliver. But the other reason this photograph is there is to remind us that on timescales of 1 million years or so, impact craters such as this are weathered and effectively removed from the geological record. In other words, we're always getting impacted by objects, but we won't see very old impact craters simply because wind and rain will weather them and remove them from the face of the Earth. So in a sense, we only see the most recent ones. So you may say, well, okay, craters on the Earth will get removed by weathering, but that doesn't happen on the surface of the Moon, for instance. Well, strictly speaking, yes, it does, but not by the same process. The moon is constantly bombarded with micrometeorites, and they will pulverize the surface and pulverize the rock such that, for instance, the footprints of Aldrin there in the photograph will eventually disappear because of this micrometeorite impact. It's even been calculated that the lunar lander and the rover and the various pieces of experiments that were left, even they will disappear under enough micrometeorite bombardment. So yes, the footprints will last quite a while, but they won't last forever, even without weathering in the sense we understand on Earth. Moving forward 10 million years into the future, Pioneer 10, I said that was going to be passing stars on timescales of order 30 to 40,000 years. So what does the 10 to the 7 signify for Pioneer 10? Well, that's the time period over which you can probably expect to still read the plaque. If any civilization picks up Pioneer 10 on its way through various solar systems, it will have travelled through hundreds, if not thousands, of solar systems by the time it gets to this time period of 10 to the 7 years. But at this point, it won't be possible to read the plaque anymore. We were just talking about micrometeorites. Well, you tend to think of space as empty, and so Pioneer 10 is travelling through the void, but in between the stars, it's not, strictly speaking, empty. The interstellar medium is full of tiny dust specks. And after 10 million years or so, impacts of these dust specks onto the plaque will mean that this plaque will no longer be readable. The intention was that the plaque would tell anybody who picks it up who we are and where we came from. A pulsar map on the left and a little cartoon at the bottom saying we came from the third rock from the sun. So if it gets picked up in a few thousand solar systems, then it might be possible for the people who pick it up to make sense of where it came from. If they don't pick it up in the first 10 million years, then it'll basically be unrecognizable. Moving forward to 10 to the 8 years into the future, we can ask about the fate of Saturn's rings. But first, it probably makes sense to ask, where did Saturn's rings come from in the first place? It's thought that maybe one of the moons of Saturn, something about the size of Mimas, maybe a moon like that got pulverized and ended up making the Saturnian ring system. When we look at a moon like that, we might think to ourselves,
that's no moon. It's a space station.
Because it does look like it's been impacted rather thoroughly by something and gives the impression of the Death Star there. But simulations have been carried out of what if we take a moon about the size of Mimas, forget the other moons for the time being. What if we were to pulverize that moon and then see what happens to the debris? You might assume the debris continues to move around the planet just like the moon did. But actually, it is not long before the debris spreads out into a ring system. Notice the timescale in the bottom right. It's only a matter of days before the interaction between all of the individual particles, all the individual bits of debris, spread out into the orbit and make a ring system. Now, over millions of years, that ring system will change because individual particles, all interacting with each other, will slowly migrate inwards. And some of them will rain down on the surface of the planet. And that's Saturn as we see it today. But that process is continuing. In other words, we can calculate that if the inward migration of particles in the ring system continues, then on timescales of order 10 to 100 million years, we would expect the ring system to disappear when all of the individual particles rain down onto the surface of Saturn. So for those of you who think that Saturn's rings are a beautiful sight in a telescope, make the most of it because they won't be there forever. Still on a timescale of 100 million years into the future, we have to remind ourselves that we can't really predict anything in the solar system. Orreries make us think that the solar system is clockwork, and when we think of a Tellurian and think of the moon going around the Earth and the Earth going around the sun, we tend to think of these things as being predictable. After all, we can predict eclipses thousands of years into the future. But that doesn't mean we can predict them millions or hundreds of millions of years into the future. That's because on these sorts of timescales, the solar system is a chaotic system. We don't even know whether the solar system will look the same. We don't even know whether we'll have the same number of planets in the solar system in 100 million years into the future. We think the solar system of the past has been different. The planets have changed order. They have possibly ejected a planet from the solar system. It's very difficult to tell. But there will be changes in the future which are totally unpredictable because, like the weather, the motion of planets around the sun is ultimately chaotic. It looks well ordered on short time scales, but it's chaotic on longer time scales such as this. Still on a timescale of 100 million years into the future. This is a little cartoon of the Milky Way galaxy, and that's where we are. There's the sun sitting in between two spiral arms in a relatively low density part of the Milky Way. But as the Milky Way rotates, the sun is going to end up moving from a low density region into a higher density region within one of the spiral arms. What's the consequence of the sun being in a high density region? It will have a lot more stellar neighbours than we have at the moment. If we think of how many neighbours do we have within a 10 light year distance of us, that number is going to increase substantially when we move into a spiral arm on these timescales. So what are the consequences of having lots of stellar neighbours? Well, one of the consequences, as we saw with the approach of Gliese 710, if stars get close to our solar system, they can nudge objects in the Oort cloud and it can give rise to a large number of comets or asteroids heading our way. Some of them are going to hit the Earth and they will cause extinction level events. This graph shows how many extinctions we've had as a function of time about 500 million years before the present, which is on the right hand side of the diagram. Notice that there are always some extinctions, but there are spikes when the number of extinction goes up significantly. And we've had a few of those spikes over the last few 100 million years. So it looks like every 100 million years or so, we get an extinction level event. The last one was the one on the right there, the KT, the boundary between the Cretaceous and the Tertiary eras. That's the one that killed all the dinosaurs. And it's probably linked to the way the sun is moving through the Milky Way, having lots of neighbours giving a much higher chance of having an extinction level event. So this, of course, is just an artist's impression of what that might look like, a large rock heading towards the Earth. In this particular case, it looks like it's heading towards Italy. Well, okay, that will be bad news for Italy, but of course, if the rock is large enough, it's going to be bad news for the entire Earth, as it will change the entire ecosystem. Species will be exterminated when this happens. What we don't know is, will that include us? Will we be advanced enough to fend off these large rocks that might be coming our way? Still on a timescale of 10 to the 8, because this is another consequence of moving into a spiral arm of the Milky Way and having more stellar neighbours. Not only does that mean it can push more asteroids our way, but more stellar neighbours means we might have a star close to us going supernova. Now, at the moment, we don't have many stars in our neighbourhood. We don't have any of them that are supernova candidates. None of them are massive enough. But if we have many more stellar neighbours when we move into a spiral arm, maybe some of them are going to be a problem for us. A supernova within 100 light years would be a danger to Earth, it's been calculated. And a supernova within 20 light years of the Earth could conceivably end all life on Earth. We know that there have been supernovae relatively close to us in the past. When a supernova goes off, it generates a particular isotope of iron called iron 60, indicated there 60Fe. And we've seen this particular isotope in sediments on the Earth. And we know that this particular iron isotope changes by radioactive decay over a period of millions of years into something else. It changes into cobalt and then into nickel. In other words, the iron doesn't survive very long on Earth. So that means if we actually see it in Earth sediments, it must have arrived relatively recently. It's not iron 60 that has been around since the Earth was born, because with a half-life of just millions of years, it would not have survived many billions of years. So if we see it in the Earth sediment, which we do, that means we must have had relatively nearby supernova not that long ago. And if it's happened before, it can happen again. And the most likely time for it to happen is when we have a lot more neighbours, when we move into one of the Milky Way's spiral arms. Still on a timescale of 10 to the 8, 100 million years into the future. The Moon has been continually robbing the Earth of some of its angular momentum. So the spin of the Earth has been slowing and the size of the Moon's orbit has been increasing because angular momentum is being transferred from one to the other. The Earth has now slowed down to the point where the length of the day is approximately 25 hours. There's no point even thinking about adding leap seconds anymore. We just have to abandon the idea of a 24-hour day. Because the Moon is moving away from the Earth, the distance from the Earth to the Moon will very soon be so large that it will be impossible to have a total eclipse of the Sun. At the moment, there's a coincidence that the angular size of the Moon in the sky is just about enough for the disk of the Moon to cover the disk of the Sun. But if the Moon gets substantially further away, then the Moon will never be big enough to cover the disk of the Sun. The best we can hope for is the picture on the right, an annular eclipse, a partial or an annular eclipse, as indicated by this astronomy picture of the day from 2020. So again, for those of you who like eclipse chasing, for those of you who like to get pictures of a total eclipse of the Sun, get in soon, because in another billion years or so, there will be none to photograph. But a more important consequence of the Moon getting further away from the Earth, not simply the lack of solar eclipses, which will be a shame, more importantly, is that the Moon has a stabilising influence on the tilt of the Earth, the so-called obliquity. Historically, the tilt has been no more than about a degree either side of the mean value of about 23.5 degrees. The cartoon on the left shows you the variation in the Earth's tilt. Very small compared to the 23-ish degrees relative to the perpendicular to the plane of the Earth's orbit. But if the Moon gets further away from the Earth, which it's going to do on these timescales, then it will no longer have a stabilising influence on the Earth's tilt. The Earth's tilt could change erratically. It could go vertical, it could go horizontal, it could take any angle in between, and hence result in wild variations in the Earth's climate. So that is almost inevitable because of the way the Moon is moving. Still on a timescale of about 1 billion years into the future, Voyager has a gold disk on board, and it's thought that this disk should survive about 10 to the 9 years or so. Remember, the plaque on the front of, on the side of Pioneer spacecraft might last for 10 to the 7 years as it goes ploughing through the interstellar medium. So why would the Voyager gold disk, indicated on the right here, survive substantially longer? Well, the Voyager disk is protected behind a cover, shown on the left-hand side here. So it's the cover that's going to take the beating from the interstellar medium and protect the record on the right-hand side. Again, Voyager will actually go through lots of solar systems on this timescale. If it's going through a solar system every 10 to the 5 years, then it would have had the chance of going through tens of thousands of solar systems before it gets to the point where, after 10 to the 9 years, the system is completely unreadable. So the disk itself might well survive. Unfortunately, the cover on the left, which is going to get eroded and pitted, unfortunately, that contains the instructions as to how to read the disk itself on the right-hand side. So although the disk might survive billions of years, unfortunately, anybody who picks this up after a few thousand solar systems, they would find it very difficult to read the instructions. Maybe they would be intelligent enough to figure it out for themselves, but they would not be able to read the manual to figure out how to read the disk. On a timescale of 1 billion years or so, the sun is going to start to change. The luminosity will increase as the sun starts to go towards the red giant phase, as the hydrogen in the sun starts to run out. Its luminosity will increase by perhaps 10% every billion years for the next few billion years. And that will drive a greenhouse effect on the surface of the Earth. The surface of the Earth might reach a rather balmy 80 Celsius. So of course mankind is going to have to figure out what we do. Going underground isn't really going to help. Maybe we'll have to leave the Earth for a while until it cools off a bit. But as the sun becomes a red giant, the sun is going to expand, and the surface of the sun is going to start getting closer and closer to the Earth. And it might be that this is a problem for us, because when you have a very large sun close to the surface of the Earth, obviously it's going to get very hot. And it has been calculated that the sun, when it goes to the red giant phase, will end up with a radius larger than the Earth's orbit. But does that necessarily mean that the Earth is going to be engulfed by the sun when the sun becomes a red giant? Well, the jury is out on that. Different people have different ideas of how to do the calculation. The bottom line is that as the sun expands, there will be a very strong solar wind from the surface of the red giant. And so the sun will actually lose mass as it expands. If there's less gravity pulling on the Earth, that means the Earth's orbit will also expand. And the cartoon on the left shows what we think might happen. As the sun expands, the Earth will actually move further away from its original orbit. So after a while, when the sun reaches its maximum size, yes, it will probably have engulfed the orbit of the Earth, the original orbit of the Earth. But the Earth has moved out, perhaps to where Mars is now. So it's not necessarily the case that the Earth is going to be engulfed by the sun. It might survive. Let's assume it does for the time being. The sun, after it's gone through its red giant phase, it will shrug off its outer layers, which will then make a nice planetary nebula, even if we can't see it from the inside. And the sun will become a white dwarf. Effectively, just the core of the sun will be left, and that's what we call a white dwarf. Essentially, a hot piece of carbon. Maybe the pressures will be high enough inside to actually form diamond. That's a hypothesis that some people have. But having survived, assuming we survive the sun going through a red giant phase, we then have to contend with the fact that the Earth will lose its magnetic field. The core of the Earth is molten because it's hot, and it's hot because of radioactive decay. It's nothing to do with radiation coming from the sun. Radioactive elements that have been inside the Earth for billions of years are producing heat as they decay, and that keeps the Earth molten. Sorry, the core of the Earth molten. But eventually that radioactive decay will no longer be enough to heat the core of the Earth to keep it molten, so the core of the Earth will solidify. Once it does that, it no longer has a dynamo, no longer has a magnetic field. It's been calculated that maybe this is what's happened to Mars. Mars is a lot smaller, so its core would have cooled down a lot sooner, so Mars would have lost its magnetic field a long time ago, and perhaps when Mars lost its magnetic field, that's when it lost its atmosphere. So when the Earth loses its magnetic field, it will be exposed to radiation, perhaps not so much from the sun, but certainly to cosmic rays. And so we would have to worry about the environment if we chose to stay on Earth after the sun has gone through its red giant phase. We'll have to worry about the fact that radiation will be pummeling the surface of the Earth. They say that bad luck comes in threes. If we survive the sun going through a red giant phase, if we survive the Earth losing its magnetic field, there's a third whammy coming along straight behind it. And that is the Milky Way galaxy is going to collide with the Andromeda galaxy. On a timescale of a few billion years, starting about 4 to 5 billion years into the future, the Andromeda galaxy is going to get very close to us, as indicated by this artist's impression. Great for those of you who like your astrophotography. You'll no longer have a telephoto lens for taking pictures of the Andromeda Galaxy. Very soon you will need a wide-angle lens to take a picture of the Andromeda Galaxy. It will pass through the Milky Way. The stars themselves are unlikely to collide with each other, but the gas and the dust of one galaxy is going to interact with the gas and the dust of the other galaxy and produce a riot of new star formation. So the skies are going to light up with the light of new stars generated when the galaxies pass through each other. They'll pass through each other and then gravity will take hold and they will gradually spend a few billion years merging with each other. And if we were to wait long enough, the supermassive black holes at the core of the Milky Way and at the core of Andromeda, eventually they will merge with each other in billions of years' time. After 10 to the 11 years, 100 billion years into the future, eventually the tug of war between the Moon and the Earth will finally come to an end. That's because at this point, one day will equal 1 month. In other words, the length of time it takes for the Earth to rotate once on its axis, 1 day, will be the same as the length of time it takes the Moon to go around the Earth, 1 month. The Earth will be tidally locked to the Moon. One side of the Earth will always face the Moon, just like what the Moon has been doing for billions of years. Remember, we can only see one face of the Moon because one face is always facing the Earth, and we can never see the far side without the intervention of satellites. The same will be true of the Earth in 10 to the 11 years. So if we still survive, if we're standing on one of the continents of Earth, then we might be able to see the Moon in the sky, and the Moon will not change its position in the sky. Whereas if we were in another continent of the Earth on the other side, the Moon would never rise. The two would be tidally locked together in much the same way that Charon and Pluto are currently tidally locked and always facing each other. We now reach 10 to the 12 years into the future, 1 trillion years into the future. If we think of what's going on around the Milky Way, we have a large galaxy surrounded by lots of smaller galaxies, such as the Large and Small Magellanic Clouds, for instance, and dozens, if not hundreds, of smaller satellite galaxies. These will all end up merging with the Milky Way, which we've just seen is going to merge with M31, the Andromeda Galaxy, but also M33 and everything else in the so-called local group. So on this timescale, the local group will be one mega galaxy. It won't actually be a spiral galaxy, that's just an icon I've placed in the centre there. What's going to happen to galaxies further away than the immediate neighbours of our local group? Well, we know that the universe is expanding from observation. We know that's true. And even galaxies that are receding from us at greater than the speed of light, they can still be imaged. As a lockdown challenge, I tried to image a galaxy that's moving away from us at twice the speed of light due to the expansion of the universe, and I managed to capture a picture of that with my camera, even without using a telescope. On the right-hand side is the Hubble Ultra Deep Field, where a small patch of sky has been imaged with the Hubble Space Telescope, and that shows us a very large number of galaxies. Many of those galaxies are indeed receding from us faster than the speed of light. It's only the closest ones that are actually receding at sub-light speeds. But there will come a time, 10 to the 12 years into the future, when the expansion of the universe, which will continue, as far as we know, for billions and billions of years to come, the expansion of the universe will continue, and there will come a point where it's no longer possible to see those distant galaxies. In other words, if we were to take a Hubble Deep Field in 1 trillion years' time, we would see no galaxies. We would just see, in this case, a couple of stars which are part of our own galaxy. And it's sobering to realise that would be the same regardless of which galaxy we happen to be a part of. So for instance, if a civilization comes into being in 1 trillion years' time, and they build themselves the equivalent of a Hubble Space Telescope, and they ask themselves, what is the universe made of? Let's look into the universe and see what we see. It doesn't matter how good their telescopes are. when they take a picture of the distant universe, they will see nothing other than the stars and objects in their own galaxy. They will come to the conclusion that the entire universe is just the galaxy that they are living in. A sobering thought. I said at the start of this talk that at the beginning of everything, it took about 3 minutes to make everything in the universe. It took about 3 minutes to make all of the protons and the neutrons, ultimately, which gave rise to all of the hydrogen which has been used to fuel the stars. So it took 3 minutes to make all the hydrogen, but now that we are 1 trillion years into the future, it's nearly all gone. So there will be no new star formation. As an aside, some people have hypothesized, well, maybe it's possible to actually make stars out of something other than hydrogen. Some people disagree. Some people say you've got to start with the lightest element. Some people say, well, maybe it's possible that you could start with heavier elements and still make stars. Maybe it's possible to have fusion reactions at the core of a star made of heavy elements, even though the surface temperature is really low. The surface temperature of a red giant might only be 3000 Kelvin. Maybe it's possible to make a star with a surface temperature 10 times lower than that. Not a few thousand Kelvin, but perhaps only a few hundred Kelvin. Is it possible to make a star with nuclear reactions at the core, but cold enough for ice to form in the atmosphere? Frozen stars. No, that's the Disney version of a frozen star. That's not what I'm talking about. If that's the picture that you've got in your head, then let it go, because what I'm talking about is stars, nuclear reactions at the core, but possibly ice in the atmosphere. Purely hypothetical, but an interesting thought nonetheless. But before we go any further, we just have to have a little aside and ask ourselves of what is happening regarding the expansion of the universe. So here's a diagram that shows the relative size of the universe on the vertical axis and time on the horizontal axis. And notice that's where we are, that's now. The universe has got a size of 1, doesn't matter what units we're using. And the 4 coloured lines are what the universe is doing, and the 4 coloured lines are different depending on how much stuff there is in the universe, how much matter, how much energy is there in the universe, because that will determine its evolution. We know that it's expanding, which means it used to be a lot smaller in the past. So if we go backwards in time, we find that the universe apparently had essentially 0 size at some time in the past, which we label the Big Bang. Now, if the universe has a great deal of matter in it, which is thought to be a possibility some decades ago when we tried to measure the amount of mass in the universe, if it turns out there's a lot of mass in the universe, then gravity will be strong enough such that the expansion will be stopped. And you can see the orange line here, the expansion will stop and then the universe will contract again until we end up with a big crunch billions of years into the future. A so-called closed universe. But we now don't think that's the case. We've now got fairly reliable evidence that the amount of stuff in the universe puts us on the red line. For a while we thought we might be on the green or the blue curve, but it now looks like we're on the red curve from measuring how much mass and energy there is in the universe. Notice that the red line is expanding and expanding and expanding and never seems to want to come back down to 0. Not only does it expand forever, but also notice that the gradient keeps on increasing. So it looks like not only is the universe expanding, it looks like the expansion is accelerating. And that's something we have yet to explain, but that's what the evidence is pointing us towards. So let's assume for the rest of this talk that the universe will continue to expand indefinitely. In order for this talk not to last another 6 hours, I'm going to change gears. Each small box in the top line is now not 10 times further into the future, but 1,000,000 times further into the future than the previous box. So we're talking about a zillion years ago. I don't know what the names of these things are. It gets crazy to start actually trying to label them with English. Let's just stick to 10 to the power, relatively big numbers of years into the future. Where did we leave the universe before we took this aside about expansion? Well, we said the universe is running out of hydrogen, and it needs hydrogen to make stars. Now, stars can last an awful long time. Stars can probably last for trillions of years, but they don't last forever. So if the hydrogen is running out, what does that mean? There will come a time when there are no more stars. The age of starlight will come to an end. When that happens, the stars will be dead, but still orbiting their galaxies. They'll be drifting through space like zombies. There will be white dwarfs, neutron stars, black holes. None of them will be generating starlight through nuclear processes. The white dwarfs are hot, and so they will shine for a little while, but then they will cool off. With no nuclear reactions to keep them hot, they will cool down. And so white dwarfs will no longer be a very good name for these objects. Perhaps we'll have to start calling them black dwarfs. Now, they'll be effectively just lumps of carbon. Some stars will be ejected from the galaxy. In other words, the interaction of stars as they're orbiting each other, they'll still have gravity even if they're not shining. Some of them will be ejected and some of them will be eaten by the supermassive black hole, hereafter SMBH, sitting at the centre of what we think is every galaxy. Magnetic fields have been mapped out in one of our neighbouring galaxies by SOFIA, the Stratospheric Observatory for Infrared Astronomy. This is the telescope that's sitting in the back end of a 747, and it's flying above most of the atmosphere to stop most of the infrared being absorbed. SOFIA has now been retired after many years of service. But SOFIA mapped out the magnetic fields, and it's thought that on looking at this particular galaxy, matter is probably being funneled along those magnetic field lines, which is how the supermassive black hole, which is at the centre of this particular galaxy, is obtaining its food. The matter that's falling into the black hole is flowing into the black hole, being steered, if you like, by the magnetic fields that exist in presumably all galaxies. What's happening at the heart of matter? Well, we know atoms are made of protons and neutrons in the core of an atom, in the nucleus of an atom, and negatively charged electrons buzzing around, as indicated by this cartoon on the right. But we think that maybe protons decay, in which case all atoms will fall to pieces. But we don't know the timescale on which that is likely to happen. Calculations in the lab imply that protons will not decay on timescales of less than 10 to the power 36 or 34, 35, 36 years. But it is possible that they decay on longer timescales. Let's assume just for the moment that protons don't decay, in which case atoms will survive for a while longer. But even if protons don't decay, atoms won't last forever, because atoms will only exist inside black dwarfs. There are no atoms in neutron stars. There are no atoms, as far as we are aware, in black holes. And so the only atoms in existence in black dwarf stars eventually will disappear because black dwarfs will evaporate. It's a quantum mechanical effect. And there will be no atoms left anywhere in the universe. Black holes will merge together. Whenever we see galaxies colliding, it looks like the black holes at the centre of those galaxies merge together. So black holes will grow by mergers and collisions. The one at the centre of our Milky Way galaxy is about 2 million solar masses. The black hole at the centre of other galaxies can be billions of solar masses. And there's no reason why these black holes don't grow to be absolutely monstrous objects that might be trillions of solar masses in mass. But black holes are not eternal. Black holes evaporate, providing that you wait for a really long time. So let's just take a little detour and ask, why do black holes evaporate? Well, quantum mechanics, a theory that's been around for 100 years and as far as we can tell hasn't given us any bad data yet. It looks like it's a really good theory that explains a lot of the quantum world. Quantum mechanics allows particles and antiparticles, or if you wish, matter and antimatter, to be made by borrowing energy from nothing, as long as the particles and antiparticles annihilate and pay back the borrowed energy. In other words, you can take energy, make some stuff, and then the stuff annihilates and makes energy again, and that pays back the original loan. How does that help us understand black hole evaporation? Well, Stephen Hawking said, what happens if a black hole, just outside a black hole event horizon, this process occurs, and we borrow energy, make a particle and an antiparticle, and then what happens if one of them falls into the event horizon but the other one doesn't? Now they can't annihilate and repay the energy that they've just borrowed. So what it looks like is that something has left the black hole, or at least the region just above the event horizon of a black hole. It looks like there's a net flux of something. We now call this Hawking radiation. It's still a hypothesis. We haven't observed it yet, but a lot of scientists believe that this will be happening to all black holes. The radiation increases with increasing mass, and so small black holes evaporate very quickly, really large black holes evaporate really slowly. So as a black hole evaporates, the radiation levels increase, which makes it smaller. So the radiation increases more, which makes it smaller, until finally the black hole disappears in a flash of radiation. Even the supermassive black holes lurking at the centres of most galaxies, even they will evaporate eventually, though it will take perhaps trillions of times longer than a black hole with the mass of our Sun, for instance. So have we reached the end of time? Well, 10 to the power 100 is a Google. That's a convenient sort of number. And no, I'm not talking about Google, the search engine. That's a different spelling. And rumour has it that they simply got the spelling wrong. They intended to go with Google, but they misspelt it. 10 to the power 100 is a Google. And after a Google years, it has been calculated that the last black hole will have evaporated, leaving no matter anywhere in the universe, just radiation. So after this point, if there's no matter left, you could say, well, nothing happens after this point. And so time becomes essentially meaningless. There will be radiation, the universe will continue to expand, the radiation wavelengths will get stretched more and more and more and more, but that is about it. And because 10 to the power 100 is a rather silly number, I don't usually spell numbers out with zeros, but in this particular case, I think we have to, just to remind ourselves just how long 10 to the power 100 years is. It's 10,000 million, 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 etc., etc., etc. A very, very long time. And of course, eternity is a very long time, especially towards the end, as Woody Allen once said. But if we need to get the meaning of human life on the perspective of these ridiculous lengths of time that we've been talking about, one of my favourite quotes is from XKCD. A human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking an email a lot. That's one way of looking at the human perspective. But rather than finish on a too depressing note, let me finish with a short epilogue. We live in a golden age. The sun is middle-aged and the sun is well behaved. The moon is at just the right distance to stabilise the Earth's axis and hence stabilise the Earth's seasons. As a bonus, it also gives us the spectacle of a total solar eclipse. Thanks to evolution, we're able to explore and discover and understand the universe. We can visit our closest neighbours by building spacecraft and sending them out, or we can build ourselves telescopes with which we can look out into the universe and see trillions of galaxies at distances of billions of light years. But this couldn't have happened in the very early universe. Humankind could not have arisen in the very early universe. We needed a sequence of generation after generation of stars needed to make the heavier elements. We need stars to take hydrogen and make helium, and then take helium and make carbon, and nitrogen, and oxygen, and phosphorus, and calcium, and iron. We need to make all the heavy elements that make us, us. And we've just seen that trillions of years from now, in the future, the universe will be dark and the universe will be boring. So you could say the best time to exist is now. Thank you for listening.